This is a lecture on spline interpolation, and spline interpolation, it's better than polynomial interpolation. It's a bit more complicated though, but let's start talking about it. A spline of degree k having knots t0 through tn is a function s such that on the interval that's closed at tn minus 1 and open at t sub I, that s is a polynomial of degree less than k, and s has a continuous k minus first derivative on the whole interval from 0 to tn. Okay, so at this point you should have absolutely no idea what's going on, but we'll make it sharp for you here in a bit. First, some observations. Splines of degree 0 need not be continuous. Splines of degree 1 are continuous, but they won't have a continuous derivative. Splines of degree 2 will have a continuous derivative. And splines of degree 3, which is what we're going to be working on, have a continuous second derivative. Okay. And so let's look at an example. This first guy, this is a spline of degree 0, and which is just a step function. Okay. This here is a spline of degree 1. And so we have, okay, it's a linear approximation, so just linear interpolation of your function. Okay, and let's look and see. We're interested in creating cubic splines, and so let's talk about the process for how that's done. We're going to talk through the process and talk about how to do these. First of all, we'll have s given our data here as we usually describe. We'll have s of x is equal to si for x element of the interval from ti to ti plus 1. So we're going to define this piecewise on the subintervals between the adjacent knots. And we're going to say that si minus 1 of ti is equal to yi is equal to s of ti. So the sk are going to match up each other along the knots. We're going to have this condition here, which is our technical way of saying that the sk prime are going to match along the knots. And we'll have this condition here, all right, which is the technical way of saying that the sk double prime are going to match along the knots. Now, these s, it's a cubic spline, so these si are cubic polynomials. Okay, a general cubic polynomial, ai times x cubed, bi times x squared, ci times x plus di. So we have 4 coefficients for each piece. We have n pieces, and so there are a total of these of 4n of these constants. Okay, we need to determine those. Now let's see the conditions we have. Okay. There are n intervals. Okay, so there are 2n conditions due to specifying what the function is on its top end. There are and its bottom end. So each of those gives us n conditions. So that's 2 n's. For the matching up conditions for the derivative, that gives us n minus 1, okay, conditions right there. So we have those. So 2n plus n minus 1 plus n minus 1 gives us 4n minus 2 conditions. But we need 4n constants. So this system is underdetermined. So what do? Well, we come in and say at the bottom end, our second derivative is going to be 0, and at the top end, our second derivative is going to be 0. So that brings in conditions. And so we've made a choice. This isn't a bad one. So you might want to remember this when you go and become an applied mathematician someday, that if you need these things to be different, you can, because we made an arbitrary choice here. Now the last box here on this slide is a handy formula for lines. I, quite frankly, had not seen this formula until I taught this course, and since I am getting, what was in my mid-50s the first time I taught this course, I don't know how this slipped past me, but it's kind of a cool formula for a line. So we're going to have it where L of little a equals big A, and L of little b equals big B. And so b minus x, b minus a. If we put in an a here, that gives us a 1, and an a here, this gives us a 0, and so that's a. If we put in a b here, this gives us a 0 over here and gives us a 1 over here, so it's b. So it's just cool. You might even be able to remember it. It's just a pretty cool formula. Okay, we're going to use it here because we're going to first set our S double prime condition, okay, because our S double prime is going to be piecewise linear. And so we can say that S double prime of x will be equal to this line function, okay, and defining it like this, they will match up, okay. And so to make this less unwieldy, set hi equal to ti plus 1 minus ti and roll that in. And so we can take this, and those derivatives are a pain in the butt, so we integrate it twice at the price of these constants on the end. Okay, if you don't believe that's what integrating does, you can do it yourself. Okay, and so now we take those and we bring in our values. We say si at ti equals yi, and si at ti plus 1 equals yi. We roll those values in, and it will give us that si of x is equal to these values here. Okay, and so the only unknowns we're left with at this point are these zi values. Okay, if we can figure out what those are, then we're done. Okay, so we take the derivative. Okay, we have these. We bring in our conditions of the derivatives matching up on the endpoints, and this will give us that this is equal to this, and hey, we can solve for those z's now. Okay, and so we can, to make this something that you can actually put on a page, we let our hi equal ti plus 1 minus ti as before. Let ui be equal to 2 times hi plus 1. Let bi equal 6 over hi times yi plus 1 minus yi. And then let vi be equal to bi minus 1. And so the equation we had on the preceding page becomes this, okay. And we can roll that into a matrix equation like so, just as pretty as you please. Has lots of zeros in it. We like the ones that have lots of zeros in them because we can solve these by some ways that are quicker than the general row reduction ways. Okay, for example, we can roll it in to this algorithm. Okay, and there you have it. And this is the complication I was talking about a spline. You're going to need a computer to do it, guys. It's complicated. It's not hard. It's complicated.